Imagine you have a grid of numbers, and you need to flip the entire thing across its diagonal. Today's problem is the transpose matrix. Take a moment. How would you move these numbers around? Before we solve this, let's start with the absolute basics. What is a matrix? Think of a matrix as a table like a spreadsheet. It has rows which go from left to right and columns which go from top to bottom. When we talk about transposing a matrix, we are essentially swapping the roles of the rows and columns. Whatever was in the first row now becomes the first column. Whatever was in the second row becomes the second column. Let's look at a concrete example. Imagine a 3x3 grid. The top row has the numbers 1, 2, and 3. In a transposed version, those numbers 1, 2, and 3 will now be the first column, running vertically down the left side. The number 4, which was at the start of the second row, will now be at the top of the second column. This might sound simple, but it gets tricky when the grid isn't a perfect square. What if you have 2 rows but 3 columns? Your result would then have 3 rows and 2 columns. The dimensions themselves actually flip. This is non-trivial because you can't just move one number at a time without potentially overwriting a value you still need. You have to be very careful about where each single element lands. In plain English, the constraint is that every element at a specific row and column position must move to a new position where the row index and column index are swapped. If an element is at row 0 and column 1, it must move to row 1 and column 0. This requires a precise coordination of indices to ensure no data is lost and every single number finds its new home. The most obvious thing to try is to simply build a brand new grid from scratch. Imagine you have your original grid on one piece of paper, and you take a second, blank piece of paper to draw the result. You would look at the first row of your original grid and write those numbers down as the first column of your new grid. Then you'd move to the second row and write those as the second column. Conceptually, you are just reading from one table and writing into another. While this works, it is inefficient in terms of memory. Why? Because you are duplicating every single piece of data. If your original grid has 1,000,000 numbers, you now need space for another 1,000,000 numbers in a second grid. This gives us a space complexity of O of m times n, meaning the memory used grows linearly with the total number of elements. The time complexity is also O of m times n, because you have to visit every single cell in the original grid exactly once to copy it over. It's a straightforward simulation, but it's redundant because we are using extra memory to store information that we already have. We are essentially renting a second warehouse, just to move boxes from one side of the first warehouse to the other, which is a waste of space if we could just move the boxes within the same room. The key insight here is that we can swap elements across the diagonal line of the matrix without needing a second grid. Imagine the diagonal line running from the top left corner to the bottom right corner. The numbers on this line stay exactly where they are. The numbers above the line just need to trade places with the numbers below the line. It's like a mirror reflection. This eliminates the need for extra space because we are swapping elements in place. Let's walk through the logic line by line. First, we determine the number of rows and columns so we know the boundaries of our grid. We use a loop to iterate through the rows. Inside that, we use another loop to iterate through the columns. But here is the trick. The inner loop doesn't start at 0. It starts at the current row index plus 1. This ensures we only look at the elements above the diagonal. If we looked at every element, we would swap them once, and then swap them back to their original positions, ending up exactly where we started. To perform the swap, we use a temporary variable. Think of this like holding a glass of water in your left hand and a glass of juice in your right. To swap them, you need a third, empty glass. You pour the water into the empty glass, pour the juice into the first glass, and then pour the water from the temporary glass into the second glass. In our logic, we store the value of the current cell in a temporary variable, move the value from the mirrored position into the current cell, and then put the temporary value into that mirrored position. This way, No data is overwritten, and we use almost zero extra memory, regardless of how large the grid is. Let's trace this on a 3x3 grid. Our grid has numbers 1 through 9. We start with the row index at 0. The column index starts at row index plus 1, so column is 1. The value at row 0, column 1 is 2. The value at row 1, column 0 is 4. We store 2 in a temporary variable. We move 4 into row 0, column 1. Then we move 2 into row 1, column 0. Now row index is 0 and column index becomes 2. The value at row 0, column 2 is 3. The value at row 2, column 0 is 7. We store 3 in a temporary variable. We move 7 into row 0, column 2. Then we move 3 into row 2, column 0. Now the first row is finished. We move to row index 1. The column index starts at row index plus 1, so column is 2. The value at row 1, column 2 is 6. The value at row 2, column 1 is 8. We store 6 in a temporary variable. We move 8 into row 1, column 2. Then we move 6 into row 2, column 1. Now we move to row index 2. The column index starts at row index plus 1, which is 3. Since 3 is not less than our total columns, the loop ends. Let's check our variables. At the start, row was 0, column was 1, and we swapped 2 and 4. Then row was 0, column was 2, and we swapped 3 and 7. Finally, row was 1, column was 2, and we swapped 6 and 8. The diagonal elements 1, 5, and 9 were never touched because the column index always started after the row index. And there's our final result. The first row is now 1, 4, 7, the second is 2, 5, 8, and the third is 3, 6, 9. The rows have successfully become columns. You'll spot this pattern when a problem asks you to flip, mirror, or rotate a grid. Look for phrases like rows becoming columns or reflecting across a diagonal. Whenever you see a request to rearrange a 2D array, always ask if you can perform a swap in place to save memory. The time complexity is O of m times n because we visit each element. The space complexity is O of 1 because we only use one temporary variable. Try the rotate image problem next. It uses this exact same transpose pattern. Subscribe for more beginner-friendly DSA breakdowns.